So in this video, we're going to be looking at another topic in basic organic chemistry, where we're looking at bond fission. Now, bond fission is basically just a fancy way of saying bond breaking. And let's say if I were to take a covalent bond between two atoms of chlorine, I've got here a molecule of chlorine. We already know that we've got a shared pair of electrons, where one of these atoms is going to have its electron shared with the other chlorine, and the other atom is going to have its electron shared with the other chlorine atom itself. Now, in organic chemistry, there's two different types of fission. There's heterolytic bond fission, and then there's homolytic bond fission as well. When we look at heterolytic fission, that covalent bond is going to break, and both of our electrons, they're going to go to the same atom, and we actually end up forming two ions. Now, in terms of a diagram, we can actually draw this process of heterolytic fission taking place using something called a curly arrow. And curly arrows in organic chemistry, they're going to show the movement of an electron pair. Now, let's say I've got a molecule here of chlorine. Chlorine is actually going to contain two electrons, one from each chlorine atom, which we've already discussed, and we can actually show a curly arrow going from the covalent bond, so these pair of electrons that we've got over here, and they're going to go to one of the chlorine atoms for heterolytic fission. So what I end up with is my electrons, they're going to be of course the start of my curly arrow, and they're going to end at the position at which they're traveling to, and so I'm going to end up with a chlorine-chlorine bond here breaking, and both of these electrons, they're going to travel towards this chlorine atom over here. Now what this means is that this chlorine atom has now gained an electron, it's got its own back from the shared pair, and it's gained the other one from the other chlorine atom, and we end up actually making two ions. This chlorine atom over here, because it's gained an electron, is going to form a chloride ion, and this chlorine atom over here, because it's lost an electron, it's got one less than it needs to, so it's going to form of course a positively charged chlorine ion. If you were to think about the charges, where have they come from? This chlorine atom has one electron less than it should do, so it forms a chlorine ion, and this chlorine atom is going to gain one electron, it has one more electron than it should do, and so it forms a negatively charged chlorine ion. And so that's how we can actually draw a diagram to show heterolytic fission taking place. What about if we were to write this in equation form? Well, we would just have Cl2, that's going to break down, and we end up with a chlorine that's going to be positive, and then we end up with a chlorine that's going to be negative as well. Now, the reason why we actually call this heterolytic fission is because if we were to look at our products, they're both going to be different. Compared to, of course, homolytic fission, our products are going to be the same. Now, if we were to look at homolytic fission, we're going to end up with a very similar process taking place where our covalent bond breaks, but this time it's going to be different because one electron goes to each atom, forming, of course, two radicals in this case. Now, a radical in chemistry, we say, is a highly reactive species with an unpaired electron. Now, let's say if I were to look at something like a chlorine radical, imagine chlorine, an atom of it is going to have the following electron configuration, where I've got 1s2, and it's going to be 2s2, 2p6, 3s2, and then of course it's going to be 3p5. We know, of course, in the p subshell and the third shell, we can actually end up with 5 electrons, and they're going to be arranged in the p orbitals, where they're like this, where we've got 2 of them, they're going to be of course paired, but then one of them is actually going to be unpaired, and because it's unpaired, it means it's going to be highly reactive, it's going to react with something, and we normally react chlorine with itself, and we end up with chlorine as a molecule, and so that's why it's going to exist as a molecule, because it's going to be stable. If we were to look at a chlorine radical, right, we've just got an individual atom, unpaired electron, it's going to be very reactive. It's going to try and gain an electron somehow by sharing, or by of course turning into an ion to become stable again. And normally in organic chemistry, we show a species is going to be a radical by putting a big fat dot next to it like this. Now, let's say if we were to draw a diagram, right, in terms of this diagram, it's going to be slightly different because, of course, previously we said that a curly arrow shows the movement of an electron pair. But let's say if we were to show the movement of one electron, because remember, one electron goes to each atom, forming two radicals, well, we can actually draw a half-headed arrow, where one half-headed arrow goes to one chlorine atom, and another half-headed arrow goes to another chlorine atom. And these half-headed arrows, they show the movement of a single electron. So yeah, this covalent bond breaks, one electron goes to this chlorine atom, one electron goes to of course this chlorine atom over here, and what we actually end up forming is two lots of chlorine radicals, which I'm emphasizing it's a radical by putting a big fat dot next to it. So yeah, I end up with chlorine that's going to undergo homolytic fission, and we end up forming two chlorine radicals. The reason why it's called homolytic is because both of the products that we form, they're both going to be the same, and that's how we can draw a diagram, and that's how we can write of course an equation for this as well. So yeah, moving on, why is this going to be very important in organic chemistry? Well, in chemistry, we already know that in order to go from reactants to products, our bonds, they need to break, and of course they need to reform to make our products. But the thing is that this process doesn't actually just magically happen. It happens through a step-by-step sequence, a series of mini reactions that make the overall reaction actually happen. Now this is what we call a reaction mechanism, and there's lots of different reaction mechanisms that you need to be aware of, and normally they involve a bunch of different things. Could be something like a radical, which we've already looked at, or it could be something like a nucleophile or an electrophile. Now a nucleophile in chemistry is defined as an electron pair donor, and it's normally going to be something with a lone pair of electrons. You can see here I've got a cyanide ion, it's got a lone pair. I've got a hydroxide ion, it's got a lone pair. I've also got an ammonia molecule which is neutral, and that's going to have a lone pair in it as well. And these molecules and ions, they can actually donate this lone pair to form a covalent bond, and that's why we actually call them nucleophiles. We can also describe them as being a region of high electron density, and they're going to be attracted to, of course, regions of low electron density. If I were to look at an electrophile, it's going to be the complete opposite. Think electro, think electrons, think phile, think loving or attracted to. We've got an electrophile, which we can define as being an electron pair acceptor, and normally it's going to be things like our halogen molecules like bromine, chlorine and iodine, or even our hydrogen halides like HCl, HBr, HI. Now there are other examples that you'll deal with when you deal with more advanced chemistry, such as, let's say, halogens that are going to be positively charged, such as, let's say, your acyl chlorides that have been turned into, of course, a positively charged ion. So you can end up with something that looks like this. You've got, let's say, an aldehyde kind of looking functional group over here, carbon oxygen double bond, and then you've got a positive charge on that carbon atom that's double bonded to an oxygen. Of course, that's going to be from an acyl chloride. It's going to be some sort of a carbonyl group. But yeah, there's other examples like carbocations where you can end up with, in this case, I've got an ethane carbocation, and there's loads of other examples that you'll deal with as well. But of course, that's for another video. Now, if you were to look at electrophiles, we can actually describe them as being regions of low electron density, and they're going to be attracted to regions of high electron density. So basically just the opposite of our nucleophiles. Now, in terms of the reaction mechanisms in organic chemistry that we need to be aware of, there's a bunch. The first one that we're going to deal with, which is of course with our alkanes, is going to be free radical substitution. The next one, nucleophilic substitution, we deal with our haloalkanes. And then of course electrophilic substitution, that's going to be with benzene. And then nucleophilic addition, that's going to be with our carbonyl compounds. And then electrophilic addition, that's going to be with, of course, our alkenes. Now if we were to break down the meaning of these reaction mechanisms, we can see here we've got substitution over here, and basically what that means is we're swapping an atom or a group with another atom or a group itself. If you look at addition, we know of course we're going to be adding one molecule onto another, and if you were to think about atom economy of all of these reactions, with addition we normally tend to have 100% atom economy. With substitution we have less than 100% atom economy itself. So yeah, that's just something to be aware of. If we were to look at the terms in them, radicals, of course free radical substitution involves radicals. If you were to look at the term nucleophilic, that basically means that of course we're involving nucleophiles. Electrophilic, that's going to involve electrophiles itself. So yeah, that's the basics of reaction mechanisms, curly arrows and bond fission when we deal with organic chemistry.